All right, in this video, we want to jump right into the thick of it and talk about the definition of the derivative. So the derivative is defined as the instantaneous rate of change of a function. So a derivative is defined as the instantaneous rate of change of a function. This can be expressed in several ways. There's just a bunch of symbols we use because historically a bunch have been used and they all kind of have unique benefits and kind of what they highlight about a derivative. So that's why we keep them around. So first we have kind of the most common we'll probably end up using in this class, which is prime notation. So you see the little apostrophe I wrote here, basically, that's prime. So we would read this as f prime of x, or f prime, if you want a shorter version. So we'll just write that. So this would be f prime. Then you can also see it as y prime. You know, if you're thinking like y equals f of x, this is also acceptable, so y prime. You could also call this first one the derivative of f of x, that's fine as well. We also have dy by dx, so that would be dy by dx, and then lastly we have d by dx of f of x. So that would be how you'd say that last one is d by dx of f of x. For right now, don't worry about why we have all these versions, but know for all intents and purposes at this point, they're identical, they mean the same thing. You can write any of them. So if we want to look into that definition a bit more, using our previous definitions where we said, here's the two-way of writing instantaneous rates of change, that's what our definition of a derivative is. So f prime of x is equal to limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. Or f prime of x equals limit as delta x approaches 0. Sorry, that one is also still needs to be fixed. X approaches a, so I'll restart saying this. F prime of x equals the limit as x approaches a of f of a minus f of x over a minus x. Both of these are definitions of derivatives. This one is the more standard, I would say. The top one is kind of our standard form, and it can be used to find a general derivative. And these two terms, the general and specific derivatives, I'll talk about in a minute. So that can be used to find a general derivative. And then this one is somewhat often called the alternate form. And it can only be used to find a derivative at a point. So the top one can be used to find the derivative of an entire function. The bottom one has to be used at a specific point. But the bottom one, the math is typically easier. So that's why we have these two. I said I would tell you earlier, that's why. Basically, the second one, the math is easier, but it's only useful in certain circumstances. The top one, the math is a little more complex, but it's you can always use it. So this is where I want to highlight what I had said there. You can calculate a derivative for either a specific point or for an entire function. So that looks like saying either the derivative of f of x is ... whatever it is, or the derivative of f of x at x equals whatever is ... So both of those are acceptable. That's why it is important that you're careful about using your language properly. You say the derivative of f of x is blank, or the derivative of f of x at x equals, say, 2 is blank. And that function, this top one here, if you just get the derivative and you don't have it at a specific point, it's going to define, it's going to be the function that's made up of all the derivatives of all the points. So for example, if f of x equals x squared, then you don't need to know how I got this, but I'm just going to tell you here, f prime of x equals 2x. So in other words, the derivative of x squared is 2x. And that means at x equals 0, the derivative of f of x, so f prime of 0, is equal to 0. So the derivative of this original function at x equals 0 is 0, because when I plug in 0 to 2x, I get 0. At x equals 2, the derivative at x equals 2 is 4, because I can get that from this equation up here as well. So if you want to find all of the points at once, you find the derivative function. If you just care about one point, you find the derivative at that point. Okay, these three examples, the first two are going to be the derivative function. And then the last one will be at a point, and you'll be able to kind of see that difference. So find the derivative of f of x at x squared minus 2x. So we start with our definition, limit as delta x approaches 0, of f of x plus delta x minus f of x over delta x. And so this is going to be the same as the limit as delta x approaches 0 of f of x plus delta x. So in other words, what I can do is I take this x plus delta x and I plug it in everywhere I've got x up here. So that's going to be x plus delta x squared minus 2 times x plus delta x. So that's the f of x plus delta x. And then I'm going to subtract f of x, which is just what I've got written up there, x squared minus 2x, like so. And then in the denominator, just leave the delta x. So we've got this all set up so far. Now the problem is, as delta x approaches 0, I've got a 0 in the denominator, so we've got to use those limit rules that we talked about, those limit techniques and strategies we used before. So what I'm going to do is I'm going to factor out a delta x from the top and the bottom. So delta x on the top is going to give me, well, we're going to have to expand this a bit first, and then I'll factor. So delta x squared plus 2x delta x plus x squared minus 2x minus 2 delta x minus x squared plus 2x all over delta x. And so what can we clean up? The minus 2x and the plus 2x can clean up the x squared, and the minus 2x squared can clean up. And then conveniently, we have lots of delta x's in here, so I can factor those out. I'll use a different color pen so you can see that I canceled these kind of second. So this delta x, this delta x, this delta x, and one of those delta x cancels. Go back to our red, and we have the limit as delta x approaches 0 of delta x plus 2x and minus 2. That's all that's left. Yes. Yes. And so then as delta x approaches 0, that means we just get f prime of x equaling to 2x minus 2. And so that's our derivative from our original function. You'll notice all I did was plug in values into the definition and then work to simplify. So I'll have another video up that's optional. That's 2 more examples, but if you feel like you got it, you can jump right in to practice.